of you and welcome to the third day of this coordinators workshop. The topic that we will cover in the morning today, this topic will be jointly covered by me and Professor Ghosh Maulik. The topic will be related to dynamics of in-visit flows, and the part 1 will be the fundamental theory and part 2 will be application to engineering devices. So let us start with dynamics of in-visit flows. We will important question, like we know that all fluids have some viscosity, right? So what is the need of studying in-visit flows? See, we all know that fluids have viscosity, and if fluids have viscosity, then is in-visit flow just study of some mathematical exercise, or there is a practical need behind that? There are many aspects of answering these questions, because this question I will like to give one or two viewpoints of looking into it. If you recall that in my introductory lecture I touched upon the concept of what is a boundary layer, and we figured out that outside the boundary layer the fluid flow acts like an in-visit flow. Not that the viscosity of the fluid suddenly becomes 0, but the flow acts like an in-visit flow. So if the flow acts like an in-visit flow in a large region in the flow field, over that large region you can easily apply the concepts of in-visit flow. If the flow acts as a viscous flow over a small region, you can have your calculations for viscous flow over that narrow region only. So that is one way of looking into it. The other way of looking into it is that sometimes for developing the theory behind the application of many engineering devices, one can start with the concept of in-visit flow and then make suitable corrections. Make suitable corrections to the formula so that they are applicable for viscous flows as well. So there are many practical issues behind even such an idealized conceptual paradigm of in-visit flow. So we will start with a very traditional exercise of writing the equation of motion for in-visit flows. See, till now the topics that have been covered, they include fluid statics. So fluid statics will mean that fluid under no shear. So there is no motion of the fluid and the fluid is in static equilibrium. Then we discussed fluid kinematics. In fluid kinematics we have discussed about the motion without thinking about the cause behind the motion. Now we are into fluid dynamics. So in fluid dynamics we will be discussing about not just the motion but also the forces responsible for the motion. Okay. So the forces responsible for the motion, when we are talking about in-visit flow, of course we are not interested about viscous stresses. We are interested about that type of force which does not give rise to any shear stress, because then that will be in the paradigm of viscous flow. So mainly the forces that will be acting in terms of surface force. So as we have discussed, in continuum mechanics there are two types of forces, surface force and body force. Surface force in in-visit flow will be due to the pressure acting on the fluid, and there will also be some body force due to gravity effect. So we will consider these surface forces and body forces and try to write equation of motion. So let us say that we have a fluid element like this, uh, this fluid element has dimensions of delta x, delta y and delta z along x, y and z. This is delta y and this is delta z. We will first write the equation of motion along x direction. So what will be the forces acting along the x direction? Let us identify the forces. The figure will be very clumsy if we identify forces in all directions. So we will identify the forces only along x direction. So to identify a forces in the x direction, see, the next question is, what we have 6 faces. Now forces in different directions, will the forces be normal to the faces or tangential to the faces? They will be normal to these faces, because tangential forces are shear forces, and then it will be the paradigm of viscous flow. It will not be anymore the paradigm of inviscid flow. So because we are talking about inviscid flow, so let us identify these 2 faces. And why we have identified these 2 faces is because these 2 faces have normal direction as x axis. Therefore the forces due to pressure acting on these faces are along the x axis. So let us write the forces due to pressure. This what is this force? Let us say that the pressure here is P. So the pressure here is P, and what is the area that on which this P into delta y into delta z. Then if the pressure here is P, the pressure here is P plus del P del x into delta x, and the corresponding area is this one. Therefore we are getting the force due to the difference in pressure across the 2 faces. So this is the surface force along x direction. What is the body force? Body force, it depends on how we are expressing it. You can express the body force as body force per unit mass or body force per unit volume. So let us say that Bx, let me write it with a different color. Let us say that Bx, body force per unit mass along x. So what is the mass of this fluid element? What is the volume of this fluid element? Delta x into delta y into delta z. What is the mass of the fluid element? That times rho, and total body force will be that times Bx. So let us write that body force here with this green color. So this one will be rho Bx delta x delta y delta z. Yes? This is body force along x. Body force has 3 components. We are writing different components of equation of motion. As I have already mentioned that we are showing the forces only along x direction in this figure. You can show forces along y direction, z direction and so on, but because these are independent equations, so for writing equation of motion along x, you require only forces along x. You do not require other components of forces. Body force may have 3 components. x component, y component and z component, but we are only showing the x component because we are planning to write the equation of motion for the x direction. So this is x. My handwriting is very bad. I can I mean, I apologize for my handwriting, but I have written it x. Okay. Now let us write the Newton's second law of motion for this fluid element along x. What is that? Resultant force along x is equal to mass of the fluid element times acceleration along x. Right? Very straightforward, the Newton's second law of motion for the fluid element. So what is the resultant force along x? Resultant force along x is the resultant force due to the surface force and the body force. So P into delta y, okay, there is one thing here, this you have P into, so here you have P and here you have, so when you subtract these two, it will become minus of del P del x into delta x and then into delta y into delta z. Okay. So this minus sign comes because this is plus and this is in the opposite direction. So if you subtract these two, then it will be minus del P del x into delta x and that times delta y into delta z. So this is the surface force and then the body force plus rho bx delta x delta y delta z. What is the mass of the fluid element? Rho into delta x into delta y into delta z into acceleration along x. If you recall the lecture of Professor Shom yesterday, then you can write the expression for acceleration along x. What is x? Del u del t plus u del u del x plus v del u del y okay. This expression was derived in yesterday's lecture. I am not going through that anymore. So now if you plug in this acceleration in this equation, you will see first thing is that one of the important things to consider is that here we have taken only P plus del P del x into delta x but not the higher order terms. The reason is, if you take the limit as delta x, delta y, delta z tends to 0, the higher order terms will go away. By thinking that we will take that limit a priori, we have not considered the higher order terms. So you can divide both sides by delta x, delta y, delta z with an understanding that they are small tending to 0 but they are not actually 0. So you can cancel them from both sides and then you can neglect the higher order terms which are of the order of squares or cubes of these, and then you will be left with, I am writing the right hand side in the left because that is the standard way of writing it, that you have rho into del u del t plus u del u del x plus v del u del y plus w del u del z is equal to minus del p del x plus rho bx. This is what? This is the equation of motion along the x direction. This equation of motion for inviscid flow is credited to Euler and it is also known as Euler's equation of motion. along x, of course, because you can write similar components along y and z. So let us write the components along y and z, given that we have derived it for x. Similar considerations will apply for y and z. I am not going into the derivation of that because that is very trivial, and we just write the corresponding terms for y and z. So for y direction, you have rho, in place of del u del t you have del v del t plus u del v del x plus v del v del y plus w and similarly for z direction, so this is y direction, and for z direction it would have been little bit more convenient had we written these equations in terms of a compact total derivative notation, but it will be easy for you to follow if we write it in an expanded form. So on the top of these two equations, so these are the y and z components, and let us on the top of that consider the x component which is here. So what we next do is that we multiply the x component with I cap, y component with j cap, and z component with k cap to write a vector, the resultant velocity. Resultant velocity is what? U I cap plus v j cap plus w k cap. So what we are doing is we are writing this I cap x equation, then y equation j cap, and this equation k cap. So let us write the x component again so that it is there in the same page, it will be easy for you to follow. Now this term you can write in this way. So this vector v is what? Ui plus vj plus wk. What is this del? I del del x plus j del del y plus k del del z. Okay. So it is clear that if you take the dot product of these two, this is how you can write it. So now what we are doing? We are considering I cap of this, j cap of this, and k cap of this, and add together. The objective is to get the equation of motion in a vector form. So to do that, if you see these three terms, if you add, what it will be? Del del t of ui cap plus vj cap plus wk cap, that means del del t of the velocity vector. So rho del v del t plus v dot del, this is ui cap plus vj cap plus wk cap, that is the velocity vector v. right hand side, this with I cap, this with j cap, this with k cap is nothing but minus grad of p, and then plus rho I bx plus j by plus k bz is the body force vector B. Okay. So this is the equation of motion in a vector form, Euler's equation of motion in a vector form. Now what we will do is, we will go ahead with this equation of motion and consider any line element dl in the flow field, and the manipulation that we will do is we will take a dot product of both sides with this dl. This dl is any line element vector in the flow field. So the manipulation is this dot dl. Can you tell that can you tell what is the objective of this manipulation? See, what is grad p? I del p del x plus j del p del y plus k del p del z, right? So let us write it including the minus sign. I del p del x plus j del p del y plus k del p del z. And what is this dl? I dx plus j dy plus k dz, right? So if you take the dot product of these two, it becomes del p del x dx plus del p del y dy plus del p del z dz. That means dp. So what is dp? dp is the difference in pressure between 2 points, differential pressure between the 2 points. So if you are interested to find out the difference in pressure between 2 points in the flow field, you can simply integrate dp. So the objective of this manipulation is to bring out a differential in pressure between 2 points. That is why we are making this manipulation. So we make a similar manipulation for the other terms, but before doing that we will be using a vector identity. This is a vector identity which you will see if you read the chapters on vector calculus in any mathematics or engineering mathematics textbook. So now, this is a vector identity. This is from mathematics. We are not going into the derivation of this. Now we will be applying this vector identity here in a sense that we will replace this in terms of this. Okay. So with this we will go to the next step which will follow from the previous step. I am just rewriting it. So rho del v del t plus half del v dot v minus v cross. What is del cross v? Curl of velocity vector, vorticity. This entire thing was dotted with dl is equal to minus dp plus. Now let us come back to the previous equation again. We have a term rho b dot dl. So what is this? Rho bxi plus byj plus bzk dot dxi plus dyj plus dzk. Now what kind of field we are considering? There may be several body forces, but the traditional example, let us take an example where gravity is the only body force. Remember, that is not necessary. That is not necessary for the Euler equation to work. It could be any body force. But as an example, we are considering that there is a body force which is due to gravity. And let us say that, let us choose our directions in a way that gravity is acting downwards, whereas the positive z axis is upwards. Okay. So gravity is acting along the negative z direction. So if the gravity is acting along the negative z direction, then you have bx equal to 0, by equal to 0 and bz is equal to minus g. Okay. So if you write that, then this bx 0, by 0, bz is equal to minus g. So this term, this total term will become what? Minus rho g dz. Okay. So minus rho g dz. Remember, one important thing is we have taken the positive z axis opposite to the direction of gravity. So the way in which we are writing the equation, it all depends on so many of these considerations. So different people could derive with different considerations. Somebody might consider that gravity is acting along positive z axis, nothing wrong with that, and will come up with a different algebraic sign. So sanctity of the algebraic sign depends on what is the direction in which you have considered the forces. So now let us simplify term by term. V dot V is what? V square, right? Yes? Minus V cross zeta, that?
Yeah, beta is it?
Yes?
What is the term?
Zeta, zeta.
Zeta, okay.
This is the vorticity. Now let us simplify these terms. I mean, this term and this term, they need not be simplified any further. We will just simplify this term. So this term is half I del x of v square plus j del y of v square plus k del z of v square dot I dx plus j dy plus k dz. this becomes half del del x of v square into dx plus del del y of v square into dy plus del del z of v square into dz. So this becomes half of dv square or d of v square by 2. So with this understanding, let us just rewrite this equation dp by rho plus g dz plus d of v square by 2. What we are doing is we are taking these two terms in the left hand side and we are combining that with this term, which eventually is d of v square by 2. So dp by rho plus g dz plus d of v square by 2. So these terms is equal to, now we take all other terms in the right hand side, so minus rho del v del t dot dl. Rho is not there, sorry, it is divided by rho already, so rho is not there. Then plus we have already divided by rho, so rho is not there. Okay. Let us try to understand this equation. We will make certain simplifications, and when we make these simplifications, we will see that what we get out of this. First simplification, we make steady flow. First simplification we make is steady flow. So if it is steady flow, then this term is not there, right? So if it is steady flow, then this term is 0. Then we will concentrate on the last term, very important term. What is dl? It is a small line element vector within the flow field. We have not specified its orientation. Now if we specify its orientation along a streamline, if we say that dl is along a streamline, so if dl is along a streamline, then you see what is this v? V is also along the streamline, because by definition the velocity vector is tangential to the streamline. So v is along the streamline and dl is also along the streamline. So this vector operation, if this vector and this vector are in the same direction, then this term will go away, this term will become 0. Okay. So that means that if you are considering the line element to be along a streamline, then this term is 0. What are the other conditions when this term is 0? One is irrotational flow. So one is dl along a streamline, the other is irrotational flow when the vorticity vector is a null vector. There is a third possibility which is very commonly neglected in books. Typically they will not write it, but you see it is a dot product of two vectors. So dot product of two vectors, that is 0 when the two vectors are having an angle of 90 degree between them, right. So if V cross zeta is perpendicular to dl, then also this term will become 0. So V cross zeta perpendicular to dl. So either of these three, you do not have to satisfy all these three simultaneously, either of these three, if it is satisfied, then this green box term will become 0, right. So we will start with one example when we consider one of the considerations to be valid, that is we consider that dl along a streamline and steady flow. So example 1, steady flow plus dl along a streamline. So then you have dp by rho plus d of v square by 2 plus g dz equal to 0. This is considered as Euler's equation of motion along a streamline. So what are the assumptions under which this equation is valid? See, not only in fluid mechanics, in any subject in science or engineering, it is important to know the equations, but it is more important to know what are the assumptions that go behind the equations. So what are the assumptions under which it is valid? What is the first assumption with which we started this chapter? Inviscid flow. So inviscid flow, let us write the assumptions one after the other. Then steady flow, and we have considered along a streamline in this example. Okay. You could further integrate this equation very easily if rho is a constant, and that integration has to be between 2 points which are located on the same streamline, because your line element is along the streamline. So you consider, let us say this is a streamline and there are points 1 and 2. So there are points 1 and 2, okay. So you can, so next what we do is that, considering rho equal to constant, integrate between 1 and 2 along a streamline. So 1 by rho, rho comes out of the integral 1 to 2 plus d of v square by 2, integral of this from 1 to 2 plus g dz so p1 by rho plus v1 square by 2 plus gz1 is equal to p2 by rho plus v2 square by 2 plus gz. Okay, which is nothing but the Bernoulli's equation. along a streamline. Bernoulli's equation is a very important equation in fluid mechanics, and we will devote some time to discuss about this equation before moving on to other examples. So first, what are the assumptions under which this final equation that we have written, what are the assumptions under which is this valid? So we will start with the assumptions which are there with the Euler's equation, plus there is one additional equation. So inviscid flow, steady flow along a streamline, and rho equal to constant. Books will write incompressible flow. It is not a correct statement in a generalized sense, because we have already discussed yesterday that incompressible flow does not necessarily mean that rho is a constant. You could also have variable density incompressible flow. So rho is a constant is a special case of incompressible flow, and we must state that if once we are bringing rho out of the integral. So one of the more common considerations, we can say that it's an incompressible fluid, so there is no interdependence of density and pressure. That much we can say. But when we say incompressible flow, that does not necessarily just mean that rho is a constant. Of course, we are meaning here not just rho is a, I mean it is good enough for us to mean that rho is not a function of P or P is not a function of rho. And that's weak sensitivity is there for an incompressible fluid. So we have discussed about the distinction between incompressible fluid and incompressible flow. So let us not go into those terminologies, that will complicate the thing. What is important for us is if rho is constant, we are taking it out of the integral. So let us better say that rho is constant. So these are the four assumptions that we are considering. Now let us divide both the sides of this equation by G, because that is a standard engineering way in which many of these equations are written. So divide by G. So what are the units of different terms in both the sides when they are divided by G? So the units, like if you consider the simplest term which will give you the unit, this is the unit of length. So what is this? Z, like you can consider it as mgz. So Z mgz by mg. So mgz is what? Potential energy. So this is potential energy per unit weight, right? So similarly V square by 2g is equal to half mv square by mg. This is kinetic energy per unit weight. So all the terms are of the form of some energy per unit weight. Energy per unit weight in fluid mechanics is often called as head. So energy per unit weight this is called as head. So these are sometimes called as, this is like potential energy head, this is kinetic energy head. So these two terms are straightforward, kinetic energy per unit weight and potential energy per unit weight. What about this? Pressure energy is a vague term. I do not understand anything by pressure energy. So it is a very vague term. If some of your students ask that, sir, it is fine, pressure energy is a very nice term, can you explain what is pressure energy? I do not understand. You will see that then you have taught your student a jargon without actually explaining what is this. So let us try to see what is the meaning of this. Now what name you will give it, cat, dog, rose or pressure energy, it is up to you. But it is important for us to understand that what is the physical meaning of this. So to understand that, let us consider a very simple example. It is an idealized example. Let us say that you have a fluid which is ready to enter a pipe. Okay. Now there is a difference between a flowing system and a stagnant system. A flowing system must possess some energy by virtue of which it can do work in presence of pressure and maintain the flow. In presence of pressure, it must do work and maintain the flow. That energy is not possessed, or that energy is not relevant when you are considering a stagnant system. So let us say that A is the cross sectional area of the pipe, and let us consider a small displacement of the fluid in presence of pressure. If P be the pressure, what is the corresponding work done? P into A is the force, that times delta x, force times displacement is the work done. So this much energy the fluid must have to sustain the flow in presence of pressure. This per unit weight, what is the weight of this fluid which is there in this region? Rho A delta x into G, right? So you can cancel delta x, A, so this becomes P by rho G, which is that so called pressure energy term in the Bernoulli's equation. So what does it say? It says that this amount of energy, the per unit weight, the fluid must have to maintain the flow in presence of pressure. This is called as flow energy or flow work. Pressure energy is a vague term and it is a technically poor term. So a technically more appropriate term is flow energy or flow work. Either you express it in terms of work or in terms of energy. So in the Bernoulli's equation, to summarize, what is the physics of the Bernoulli's equation? The Bernoulli's equation is having three energy terms, which in summation is called as a mechanical energy. So what are the three energy terms? One is the kinetic energy per unit weight, another is the potential energy per unit weight, and the third term is the flow energy. So the fluid, when it is being transmitted from one place to another, when the fluid is being transmitted from one place to another, then this sum total of these three energies is remaining conserved. It is important to understand that this mechanical energy conservation principle, this is not the energy that is possessed by the fluid, it is the energy that is transferred by the fluid. Let us consider an example. Let us say you have a conveyor belt like this. You put your suitcase here on the conveyor belt and the suitcase in the next moment is transferred to this. This suitcase is like a packet of energy. It has kinetic energy, potential energy and flow energy. Is the belt possessing the suitcase here? It is not really possessing the suitcase, it is continuously transferring the suitcase. So the belt is like a flow field. So what is happening is that the flow field is transmitting the energy in such a way that sum total of kinetic energy, potential energy and flow energy, which is also the total also called as mechanical energy, is getting conserved in the absence of any viscous dissipation. This is what is the physics of the Bernoulli's equation. Okay. Now when we have considered the example 1, we have, what was the example 1? Steady flow and dl along a streamline. We consider example 2, steady flow plus irrotational flow. Okay. So steady flow plus irrotational flow, let us bring back the equation, the general equation which is given in this box here. For irrotational flow, so for steady flow this brown colored circle expression will be 0. For irrotational flow, because this vorticity is 0, null vector, this term, the term in the green box will be 0. So the equation that we will get back is the same equation, same Euler's equation, but only difference is that in the previous case the Euler's equation was applicable only along a streamline. Now it can be applied between any 2 points in the flow field provided the flow is irrotational. So, and if you are integrating it with constant density, then you can also get the Bernoulli's equation. So for the steady flow plus irrotational flow, you can, if it is in addition inviscid, and constant density, then we can apply Bernoulli's equation between any 2 points in the flow field. The 2 points may or may not be located on the same streamline. So if we are considering flow, if we are considering 2 points along a streamline, then you can use the Bernoulli's equation with all other restrictions valid, but it is not irrotational, that is okay. But if it is irrotational, then the 2 points 1 and 2 need not be located on the same streamline. Okay. So irrotational flow is a very special case where between any 2 points you can use the Bernoulli's equation provided other conditions are satisfied. Now irrotational flow is a very special, is a very peculiar type of flow. I am not going into the details of this because possibly Professor Ghosh Moulik will cover that in one of his lectures towards the end of this course. But we have to understand that irrotational flows are interesting because irrotational flows may not always remain irrotational. Initially if the flow is irrotational, but finally the flow may not remain irrotational. So let us consider a classical example. Let us say that you have a solid boundary like this. And fluid is coming from far stream with uniform velocity u infinity. Is this flow rotational flow or irrotational flow? This one. This is irrotational. Curl of this velocity vector is a null vector. This is irrotational flow. Okay. Now what we have discussed in the first day of this workshop is that you will see that because of the effect of the wall there is a velocity gradient that is created. There is a gradient of velocity along the cross stream direction that makes this flow rotational. So there was an initially irrotational flow, but effect of the wall or the viscous effect has made it rotational. How to understand it physically? I am giving you a very simple example. Let us say that you are traveling by a bus. You are traveling by a bus and you are moving with the bus with certain speed. Now the bus is coming close to the stoppage. when the bus is coming close to the stoppage, what is happening? You are very anxious, you want to get down of the bus. So many of us, what we do, even if the bus has not stopped, we try to jump out of the bus. And to make sure that we don't fall, we try to move along with the bus so that we are not disturbed by the change in speed so quickly. So once you are jumping out of the bus, you will see that you are having a tendency to fall, tendency to topple. To overcome the tendency to topple, actually you are trying to maintain your velocity in a certain direction. So the motion of the bus is like the flow field, and the road is like a wall, a solid boundary. So because of the presence of the wall, you are not already previously having a rotational effect within you as you are moving. Now suddenly if you come out of the bus and you are in touch with the ground, you feel that you are having a tendency to topple. So that means that there is a rotationality that is imposed by the effect of the wall. Okay, so the effect of the wall is felt by the fluid because of viscosity only. So what are the factors that can make? So we can say that your motion was like a flow field, and the solid boundary, the road, is like a wall. So that will make an originally irrotational flow a rotational one. So that means, what are the factors that can make irrotational flow rotational? We will identify some factors. Because of lack of time, we cannot discuss about all these factors, but it is important because these factors are prevailing in nature very commonly. So it is very common that originally irrotational flows become rotational. So presence of solid boundary I am identifying some other points. Thermal stratification, so thermal stratification means you have, because of density variation, the temperature variation across different layers of fluid. That is what is thermal stratification. Shock wave, at least all of you have heard the terminology of a shock wave in a compressible flow. So you have abrupt discontinuities in the properties of the fluid as you confront a shock, and then across a shock wave can convert an irrotational flow to a rotational one. And Coriolis force. So Coriolis force is felt when there is a translation of a fluid in a rotational reference frame. In a frame that is rotating, let us say earth, then let us say there is a river that is translating on earth. So earth is rotating and there is a river which is translating relative to the earth. So that experiences a force. Because of that, certain ocean currents will move in a certain direction in the northern hemisphere and they will move in a certain direction in the southern hemisphere. So that can convert an irrotational flow to a rotational one. So you can see, this is just to highlight that there are abundant examples in nature which can convert an irrotational flow to a rotational one. So if you have an irrotational flow will remain irrotational forever. See, thermal stratification, shock wave and Coriolis force are not very common examples that we are encountering in engineering, but presence of solid boundary is a very common example. So presence of solid boundary will convert an irrotational flow to a rotational one provided the fluid has viscosity. So if the fluid has no viscosity, although there is solid boundary, the effect of solid boundary will not be propagated into the fluid. So if the fluid is not having any viscosity, then irrotational flow will remain irrotational forever. So this is like a combination of irrotational and inviscid flow. Uh, so this is the example 2. I will consider an example 3 here, again coming back to this equation. Now let us say that you have a flow along a streamline but unsteady flow. So example 3, unsteady flow along a streamline. So for flow along a streamline, this term in the green box is 0, that we have already discussed, but for unsteady flow this term will not be equal to 0. So let us write this term minus del V del T dot dl. So for a flow along a streamline, we can write the velocity in terms of the unit vector along the streamline, which we call as epsilon s. So we can write V is equal to V epsilon s. And dl is this one, where ds is the elemental length along the streamline. Now everything is along the streamline. So del V del T dot dl is equal to minus del V del T ds. So your equation becomes dp by rho plus g dz plus d of v square by 2 is equal to minus del V del T ds. If you have constant rho, constant rho, so you can see that this is like the Bernoulli's equation, but you have one additional term due to unsteadiness. This is known as unsteady Bernoulli's equation. Okay. So to summarize what we have discussed so far, we have discussed about Euler's equation of motion and its simplification to a special form known as Bernoulli's equation, and the assumptions under which that equation is valid, and the physical implication of different terms in the Bernoulli's equation. We will wind up, but before that we will work out a very simple problem to demonstrate the use of the theory that we have discussed so far. So let us consider a problem. Let us say that you have a two-dimensional flow field with u equal to ax and v is equal to minus ay. Okay. What is the difference in pressure between 2 points 1 and 2 in this flow field, assuming density as constant? You can assume that rho is equal to constant. Okay. Now there are several ways of working out this problem. Let us try to first get an insight of what is this type of flow. Physically, what type of flow is this? So first of all, given any flow field, we must try to see that whether it is satisfying the continuity equation. We are given that rho is constant, so it must satisfy the incompressible form of the continuity equation, and because you have two components of velocity, you have two dimensional incompressible flow. So two dimensional incompressible flow so this is what we now must check. So you have u equal to ax, so del u del x is a, and v is equal to minus ay, so del v del y is minus a. Okay. So this is incompressible flow. What about the rotationality? What is the angular velocity with respect to z axis? What is the angular velocity? This one, right? This is 0. So that means you have irrotational flow. What is the rate of deformation? Rate of angular deformation? This is also 0. So it is a very peculiar example when the fluid is not changing its volume, it is not rotating, it is not having angular deformation, right? So physically what is it doing? So to understand that, let us try to get the equation of the streamline. So equation of streamline. See, these are not required to solve the problem, but always try to understand one thing. Solving a problem for an answer is one thing, but developing an insight on a given problem and demonstrating that to your students is really a good job that a teacher will do. Not just to get the final answer of the problem, but give a more detailed physical insight on the problem that you are addressing. So what is the equation of streamline? Dx by u is equal to dy by v. This is the equation of the streamline. So dx by ax is equal to dy by minus ay. That means you can cancel a and integrate ln x is equal to minus ln y plus a constant of integration which we call ln of c. That means the equation of the streamline is xy equal to c, which is what? A rectangular hyperbola. So let us try to sketch the streamline. These are the streamlines. What are the fluid, what is the fluid element that is doing in the streamline? Originally the fluid element was like this. Now as it is moving, what is happening? Its volume is remaining conserved and it is moving along the streamline. That means what is doing? It is along x, it is getting stretched. If it is getting stretched along x, it must get compressed along y, right? So we are just drawing another configuration which is something like this. This shaded volume and this shaded volume is the same. This you can see, this fluid element is neither rotating nor having angular deformation. It is simply getting stretched along x and compressed along y such that its volume is getting conserved as the flow is taking place along a streamline. The equation of the stream function, the equation of the streamline is xy equal to constant. So this is the physical picture. So this is the kind of flow. Now we make the two assumptions to complete the solution of the problem. One is viscosity equal to 0 and the other is rho is constant. This is an inviscid flow. So if the flow is irrotational, we have checked that the flow is irrotational, then it will remain irrotational forever, right? So we have discussed this very important concept that if the flow is irrotational, it will remain irrotational forever until and unless those few effects that we have brought in will come into the picture. So one of the important effects is the viscous effect. So if viscous effect is not there, then irrotational flow will remain irrotational forever. That means we can safely apply for constant density the Bernoulli's equation between any 2 points 1 and 2. Okay. So to find out the pressure difference between 2 points 1 and 2, we can simply use Bernoulli's equation no matter the points 1 and 2 are located on the same streamline or not. So P1 by rho plus V1 square by 2 plus GZ1 is equal to P2 by rho plus V2 square by 2 plus GZ2. Assuming that Z1 and Z2 are same, there is no change in height, you can cancel this. So P2 minus P1 by rho is equal to V1 square minus V2 square by 2. What is V? V is U, V square is U square plus small v square. That is the resultant velocity. So a x square plus minus a y square. So a square into x square plus y square. So P2 minus P1 by rho is equal to a square into x1 square plus y1 square by 2 minus a square into x2 square plus y2 square by 2. Which one? Which one, minus or plus? I think it's all right. Yes? Minus the square, it becomes plus. Okay. So what we can see here is that by a very simple consideration, we can get the pressure difference between 2 points. I will leave you as an exercise that using Euler's equation, how can you find the same answer? That means instead of using this consideration, you start with the Euler's equation in differential form. You find out del P del x and del P del y and find out the pressure difference dP as del P del x into dx and del P del y into dy. And then you see, you check by integrating that the pressure difference that you get from the differential form of the Euler's equation is same as this final answer. That is a long way of solving the problem. This is a short way of solving the problem. Of course, you have to be assured that the flow is irrotational. So I think this is what I intended to cover for the dynamics of inviscid flows. I think we will be having a tea break now, and after the tea break, Professor Ghosh Maulik will take over. Thank you.